Welcome to this video in which we will be talking about nested quantifiers, um, their meaning, their expressivity power, and what would happen when we have a negation of nested quantifiers. How can we deal with it, rewrite it in terms of um, quantifiers being applied on a negation of a certain formula. So, nested quantifiers are often necessary to express the meaning of sentences in English, as well as important concepts in computer science and mathematics in general. Example on this is the following expression or sentence. Every real number has an additive inverse. So this can be written as for every x, there is a y where the domain of x and y are the real numbers. So for every x, there are some y's such that x plus y is equal to 0. We know actually from arithmetic that in this case y would be equal to minus x, which is the additive inverse of x. And of course, x is equal to minus y. X is also called the additive inverse of y in this case. So notice how we nested the quantifiers in a very specific order. Okay, so since the sentence was saying that every real number has an additive inverse, so there exists another element such that that element is the additive inverse. So we nested the quantifiers in this order. So a universal quantifier at first, and then an existential one, and then the property afterwards. Okay, and the property here is a property that link x to y. It's a relation between x and y, or a predicate that applies on x and y, and it yields true in case x plus y is equal to 0. Okay, so we can also think of nested propositional functions when we actually replace a whole part of the quantified expressions by another predicate. So actually, we could put the parenthesis on the first chunk, on the second chunk of the expression to say that for every x, there is a property q that is true for x. And that property q means that there must be a y such that p of x and y is true. And here, the p of x and y is x plus y is equal to 0. Okay? But so often we will clarify and explicitly mention all the nested quantifiers that are identified in the sentence, kind of unfolding them, clarify them, explicit them, so that we can afterwards reason about the truth of these quantified expressions with when combined with other expressions. So we will see this that this is necessary when we work on the translation from English to logical expressions, and then the analysis of those logical expressions to check whether they are equivalent or not, or to make certain inference from them. So the inference in logic is our next step in this course. Let's see a few additional examples, rules, and laws that should be respected when it comes to nested quantifiers. So the first concept is that the order of the quantifiers really matters. So if you have a certain property, such as p of x and y is true whenever x plus y is equal to y plus x, and where the domain of x and y is the set of real numbers, then actually I think you can say that for every x and for every y, the property p of x and y holds. Okay. This is true because the plus operator, it's known to be commutative. Okay, so x plus y is y plus x. It's due to the nature of the addition. Okay, and this also comes from the fact that um, if you add y1s to x, so if you add only 1 to x, then you get the successor of x. If you keep adding ones y times, you reach the y's successor of x among the list of integers. But if you do the same, if you start from y and you keep adding x ones to it, you reach the same value. Okay, so it's due to the nature of the natural integers, or even real numbers. Actually, it applies also to obviously to real numbers, and to the nature of the plus operator that is commutative. Okay. Um, so what if someone would say the following: for every y, for every x, p of x and y is true? Don't you think that this also holds? Okay. Well, actually, the order here does not really matter. And the reason is that your property uh, is kind of symmetric. Okay. Um, so it's like the friendship relationship. It's a symmetric relationship. If A is friend with B, then B is also friend with Y. Okay. This is why we can interchange the order of the quantifiers, but this is not the only condition. The other condition is that both quantifiers are universal. So um, we are saying that for every y and for every x, you could also say for every x and for every y. Okay, uh, so since we have two universal quantifiers, we can interchange their order. Okay. This also happens when you have two existential operators. We will see it in a couple of examples later on. Okay, but when you have, for example, universal and existential quantifiers that are nested within each other, then the order really matters, even if the property is kind of symmetric. So let's consider this one. The relation Q of x and y holds whenever x plus y is equal to 0. Okay, so Q of x and y means that the sum of x and y is equal to 0. Again, the domain is for x and for y is the set of real numbers. So what about the this expression? For every x, we can find a y such that I'm sorry, I have to change this into Q, such that the Q of x and y is true. Well, actually, I think this holds because um, the additive inverse always exists. So that's why we can pinpoint it that y is equal to minus x. Okay, so it's sufficient to consider y to be equal to minus x. In this case, x plus y would be equal to x plus minus x, and by definition, the additive inverse, when added to the original element, would yield 0. So we can clearly say this about um, um, uh, q of x and y. Okay, we can say that for every x there is a y, but we cannot say the inverse. Okay, of the nested quantifiers. Okay, we cannot say that you can find a particular y such that, let's call it y0, such that no matter what you add to it, you will get 0. Maybe this you can say it for the multiplication. Huh? There is a particular y which is 0, such that if you multiply it by any other number, this would yield 0. But we cannot say this about the addition operator, about the summation operator. So once again, here I have to say Q. I will correct this in the slides and re-upload them on Moodle. I'm sorry for this. Um, and I just want you to notice that the relation itself, it's kind of symmetric because the presence of x and y So if the summation of x plus y is equal to 0, then it means that the sum of y and x is equal to 0. So the relation itself is symmetric. Okay, so if the q of x and y are true, okay, well, this means that the q of y and x is also true. Okay, uh, because the plus operator is commutative, and this expression is equivalent to that one. Nevertheless, the order of the nested quantifiers really matters. The first sentence is saying something completely different from the second one. Okay, so pause the video, meditate these two formulas, and think about them. Okay, so I'm gonna repeat their readings. For every real numbers, you can find an additive inverse for that number, and this always exists because it's sufficient to consider minus x. But on the other hand, we cannot say that there is a particular number so that when you add another number to it, any other number, okay, any other number, you will obtain finally 0. This does not hold, okay? There is no such a magical y0, so that when you sum it up with any other number, you would get 0 at the end, okay? Only one of these axes would apply, which is minus y0, okay? If y0, let's say, is equal to whatever number, like uh, let's say 5, okay? If you sum it up with minus a 3, you won't get 0. If you sum it up with 1, okay? So only one x, which is equal to minus y 0, okay? So only minus y 0 satisfies this condition. All the other actually x's that are different than minus y 0 do not fulfill this condition q of xy or q of yx, okay? So the relation is symmetric. Nevertheless, the order of the universal and existential quantifiers, they really matter, okay? Great. So let's consider more examples. So let u be the set of real numbers, and let's define p of x, y to be the product of x and y is equal to 0. So p of x and y holds whenever x multiplied by y is equal to 0. So let's check the various combinations of nested quantifiers and reflect on their truth value. So what about this one? For every x, for every y, their product is guaranteed to be equal to 0. Think about it. Okay, so I think that you agree that this cannot be true, because you can, okay, so actually to show us this, it is sufficient to find a particular x, okay, and a particular y such that not p of x and y. And you can find these actually. For example, 2 and 3, their multiplication is equal to 6. It's not equal to 0. Okay? And you will see when we will talk about the negation of nested quantifiers, you will see this rule almost towards the end, but I'm going to evoke it right now because it's going to help me show you the correlation between the various formats and how to prove or refute a certain format, okay? So this is equivalent to the negation of this one, to not the case that for every x, for every y, p of xy, okay? So why they are equivalent? Because you will see that the rule for the negation when you have nested quantifiers is like the rule for one single quantifier. So an intermediate step is the following: not for every x, for every y, p of xy is equivalent to for every x, there exists an x such that not for every y, p of xy. Okay, so we consider this part as one single formula, and we get the negation inside. As you remember from last video, this flips the quantifier and gets the negation inside. And now we can do this once more, and then we get to this format here. Okay, so this is going to flip this quantifier into an existential one, and then put the negation inside its scope. Okay, so if it is not the case that for any two real numbers, their product is equal to 0. To prove this, you need to show us that this is equivalent to showing us that for two particular values, at least two particular values, it's not true that their product is equal to 0. And you can easily find those x and y. Just consider x0 equal to 2, as I said, and y0 equal to 3, or any other two numbers whose product is not equal to 0. Good. What about this format? If you pick up any x, you can find a y such that p of x and y is equal to 0. What do you think about it? Can't you find that particular y? So I have just discussed this in the previous slide, okay? So this is true because no matter what you pick as a value for x, you can find y0 particularly that is equal to 0, such that the product of x and y0 holds, okay? And that y0 is sufficient to consider the value y0 equal to 0 to let it work with any other number, okay? Don't forget that the 0 is considered the absorbent element in the multiplication operator with respect to the multiplication operator. Let's consider this form. You can find an x such that no matter what you pick up as a value for y, that x multiplied by y would end up having a 0 as a result at the end. Well, it happens that this is also true, don't you think? Okay, so it's sufficient again to consider x0 equal to 0, so that no matter what other value of y, the p of that particular x0 and y would be would end up being equal to 0. Okay, perfect. What about the last format? You can find a certain x and a certain y such that their product is equal to 0. Well, absolutely. You can consider x and y equal to 0, or x equal to 0 and y equal to anything you want, or vice versa, y equal to anything you want and x equal to 0. Okay, so it's really easy to show this. Okay, when you have fully existential quantifiers, the sentence would just talk about a certain combination of x0, y0, etc., that would satisfy your predicate. Okay, so no matter what the value, so as long as you have just existential operators, then your statement is just checking the existence of a certain tuple of variables that satisfies your predicate. Okay, so please reflect on these properties, apply them also on the examples from the previous slide and on examples from the book or from your imagination actually, and try to get a deeper understanding of how we nest these operators. So the general rule is we are giving the rule for two variables, okay, for two nested quantifiers, but you can generalize it for any sequence of nested quantifiers. If you have for every x, for every y, a certain property on x and y, well, in this case, this is true if and only if it's true, the property is true for every pair of x and y. And this is why if we swap the order of for every y and for every x, this also works the same. It is false when there is a pair of x and y such that p of x and y is false. So it's sufficient to find a pair of x and a y such that not p of x and y. Okay, so this is equivalent to not the for every x, for every y, or for every y, for every x, the property p of x and y is true. Okay, for every x, for every y, the property of x and y is true. Okay, so this is equivalent to there exists, and a negation inside. Let's consider the dual, which is you can find x and y such that the property of x and y holds. This is similar to finding y and x. Okay, so it's true whenever you can find a pair of elements x and y such that p of x and y is true. And to refute this property, to show that it's false, it's really hard because you have to show that p of x and y is false for every pair of x and y. Okay. In the middle, so yeah, just to show you the equivalence of this formula with universal quantifiers. So actually, this is equivalent to say that for every x and for every y, the property does not hold. You don't have p of x and y. Okay, so this is the equivalence of not there exists an x and there exists an y, such as p of x and y hold. Okay. Uh, what about the two other formats? So either you have for every x there exists a y, or there exists an x such that for every y. And these two have different meanings between each other and between them and the first and last statements. Um, to refute this format, you have to show that you can find at least one particular x for which, no matter what the y that you pick up, the property does not hold. So the negation is this one. And the negation of the third line formula is the following. So the negation must be something like for every element, you can find a counter example. You can find a y such that the formula does not, or the predicate does not hold. Okay. So you will see the negation rules at the end, but I think we don't need them anymore because we have just explained them right here. Okay. And just again, please pay attention to the difference between these two formats. Okay, just pick up any predicate. So for example, if P is about the friendship of X and Y, this sentence here is saying that every person has a friend. The sentence here is saying something different. It's saying that there is someone who is a friend with everyone else. So even if the friendship relationship is symmetric, because if X is a friend with Y, then Y is also a friend with X. But the two sentences, they are saying something completely different. Okay, so replay the video to check my readings for them, come up with your own examples until you get the ideas. And of course, you will have several examples in the upcoming slides. So how can we translate the following? The sum of two positive integers is always positive. The sum of two positive integers is always positive. Well, usually when you do such translations, you have to make it gradually. So you have, first of all, to rewrite the statement to make the implied quantifiers explicit and also the domains of the variables clear. So for example, a rewriting while preserving the same meaning for the sentence would be as follows. For every two integers, so we explicit the domains here, for every two integers or two real numbers, if these integers are both positive, and this is a property on those integers, so it's two predicates, positive of x and positive of y, that we can also simply write as x is greater than 0 and y is greater than 0. Then, so we have an implication. If we have these two premises, then necessarily the sum of these integers is positive. We necessarily have x plus y strictly greater than 0. Okay, and this is for every two integers, x and y. So for every x, for every y, as long as domain of x is equal to the domain of y is equal to the set of natural integers, or integers in general. Actually, it could be this set z. Okay. Yeah. So let's check the details and how to get to that version. So actually, you can further refine your sentence to introduce the variables x and y. So for all positive integers x and y, x plus y is positive. Or for all integers x and y, if x is positive and y is positive, then x plus y is positive. So the result would be something like this. Okay. Of course, if you pick up the domain carefully, so that the domain of x is equal to the domain of y is equal to n star. Okay, all which is equal to n minus the 0 element. Then in this case, you can say for every x, for every y, simply, okay, after this reduction of domain, you can just say that the property x plus y, I'm sorry, x plus y is strictly greater than 0. Okay, because your elements x and y already satisfy these two conditions, okay, if you restrict the domain. But if you keep on all the possible integers, then you have to fine tune your elements, okay, in order to talk about this property. What I'm doing here is quite similar to the example of student in a class and the student ha, who has taken a Java course. If you restrict the domain to be solely the students in your class, then you just talk about the Java property. But if you consider all the students in your university or in general, then you have to add further tuning to say that that element is a student in your class, and only then the property Java of X would be true. Okay, so here we have the same two possibilities. Don't worry if you're used to determinism in mathematics and uh, you're used to having only one solution for every single problem in mathematics. I totally agree with you. But when it comes to a modeling effort, as we are doing here, we are modeling a real life concept, a real life scenario, an idea that we have in mind with a mathematical tool, typically here, logical formulas. So when you do so, since it's a modeling effort, then it's normal to not have one single solution. There is no harm in this. Okay, it's up to you to work out your skills in being flexible and able to represent it in several different ways. And then when it comes to which way to choose, I recommend the most detailed ways where you explicit all the predicates and where you consider the most general domain U, okay, universal domain U, unless it's stated differently. Because when you make your domain the widest possible domain, then you obtain sentences that are talking about the same x's and y's, okay? And you use the predicates to further tune or subset the set U, okay? Each time you subset it in a different way, you get a certain implication or a rule about their properties. And then when you model a certain system or a set of properties or a bunch of flows, etc., you can create coherent sentences that are using the same predicates and where the variables belong to the same big set. And only then you can reason about those formulas and conclude something coherent from them. Okay. Let's consider another example, and you will see how flexible it is to represent this example. So, sorry, how flexible you can be while representing this example, and it only depends on what you want to do next with your expressions or formulas. So, for example, we want to say that there is a woman who has taken a flight on every airline in the world. Okay. So one way of representing this is to consider the as a domain of W, the set of women who traveled on at least blah 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 blah. Okay, one airline, and then in this case you just have to say that there exists a W actually such that um, uh, taken a flight on every airline of W is true, something like that. Okay, so if you consider, let's say, without restricting the domain, if you consider the set of all women in the world, you can just invent one predicate that woman has taken at least one flight on every airline. Okay, and you embed all these characteristics within this predicate. Okay, but clearly this predicate, if you check it, it has the word at least in it. Okay, so at least one flight. Okay, so uh, that woman has taken at least one flight. Okay, so there is one hidden quantifier on what? On every airline company. So there is another hidden quantifier here. So this is why, although this is somehow correct, but it's not satisfying because your predicate is still hiding complex quantifiers in it. Okay. So what is the cost of introducing these intermediate quantifiers on the flights and the set of airlines. Well, actually, the cost is to introduce more predicates, okay? So another extreme is to really explicit everything, like all the details. For example, I can say that there is a woman W, such that so I can consider W to be in the set of all people on Earth, and in this case I have to say that W is particularly a woman. So we can imagine that woman of a certain person W is true only when W is a woman, okay? And so there is a woman who has taken a flight, so I can use has taken flight, that woman a flight F, but what about that flight? So there exists a flight F, okay? So I cannot keep a variable here. So there is a woman and there is a flight such that that woman has taken a flight F, and actually I should show that that flight could be operated by any airline company, okay? So I need to talk about the flight and the airline company at the same time, okay? So, well, the flight is related to the airline company because it is operated by that airline company. So I need to mention this before talking about the flight. So I need to add a T. So there is a woman W such that for every airline company A, okay, there exists a flight F, okay, so I'm gonna remove also the F from here, such that is operated this flight F by that airline company A, okay, and that woman has taken that flight F. So there is at least one flight from every airline company such that that flight is operated by that airline company and that woman took that flight, okay? So do you see in this case the domain of W can be people, all people on Earth, or any person, okay, or human being, okay? Because I'm using this predicate to further specify that W is a woman. The domain for F, it could be any flight, okay? And this is why I'm using this, I'm sorry, this predicate is operated to further specify whether the flight has been operated by airline A or airline B, etc. Okay, and the domain for A is all the airline companies. Okay, airline companies, which are okay. So any airline company. So I'm talking actually about the correlation between W and F in the last predicate to specify that W has taken that flight F. Okay. So intermediate solutions could be something in between. So I could, for example, limit W to be just set of women. And I can use a predicate. Okay, so I still need to designate flights and airline companies, but I can use a smarter predicate called has taken and it takes a variable W, a flight F, and an airline company A to say that that woman took a flight F on that airline company. Okay, if I use this combined predicate on one hand, and if I restrict the domain to only women, then I can say right away the following short version. Okay, there exists a woman W such that for every airline I can find the flight such that that woman has taken that flight from that airline company. Okay, so and this is the version that is used in the slides, but actually if you fine tune your domains, or you change them somehow, you relax the constraint on one of the domains. Well, you need to constrain your variables with additional predicates, such as here. You could also introduce intermediate predicates to talk about the binary correlation between flights and airlines before talking about the correlation between the woman and the flight. Okay, so all these versions are okay, but maybe this one here and that one there, they are okay. Okay, but this one here, it's not very good. Okay, because it's hiding inside it, inside one of your predicates, it's hiding the words at least and for every. Okay, so we really need to explicit these quantifiers, and if you do them, then it's really cool. So by the way, even if I'm adding the for every A and there exists an F inside the formula, but since I have a conjunction, then I can actually put them outside. So this formula, he can be rewritten as there exists a woman W, such that for every airline, there exists a flight, such that, and I repeat the same predicate. So woman of W is true and has taken the woman the flight F and is operated the flight by the airline A. Okay, so no problem. Okay, so you can use this format or that format on the top, they are equivalent, or you can use this version of the domains and the predicates. So version number, let's call them 1, version number 2 are okay, but version number 3 is not really good. Okay, so you have, of course, all the details in the slides. You can check them on your own. Okay, it's the version number 1 that is mentioned here in the slides. Let's do the reverse with a couple of examples. Let's translate from nested quantifiers into English, and this is really a very good exercise for you. So here we have this sentence: for there exists an x such that for every y, for every z, if f of xy and f of xz and y is different than z, then necessarily not f of yz. What about these predicates f and the domains of x, y, and z? Well, actually, it seems that the domain of x, y, and z is the domain of persons, okay, in general, people. And f of x and y is true if and only if x and y are friends, okay? Well, now this makes a little bit more sense, okay? Well, they are restricting actually the domain to the set of all students in your school, but you can also generalize it to people or persons really as you like. So now let's try to read this sentence. Okay, well, actually you can always make a straightforward reading that is a little bit boring. Okay, so there exists a student such that for every other students y and z, if x is a friend with y and x is a friend with z, and y and z are not the same student, okay, just be patient, I will get to it, then y and z are not friends, okay? But yeah, so you can do this straightforward reading if necessary, just to guarantee that you will get the full grade because you're making a good guess here. Just you have to pay attention to the parentheses, to the conjunctions, etc., and how you read the implication. But you can do this quite technical reading of the sentence. But then after you understand it, it's really cool if you can, and sometimes this is really necessary to get the full grade, or if you have multiple choices and you have a better choice or a more concise choice and that you are asked to select, then it's good to know that you can represent this or translate this formula in a more concise way in English. So don't you think that the same sentence is saying that um, there is a student, okay, um, whose friends, okay, whose friends, any friend, okay, any X and Y, are not friends with each other, okay, something like that, okay. So I think you can, after you understand, you make the basic understanding by making the straightforward reading, you can make an effort to simplify the sentences, particularly if it is required in a question or in an assignment or an exam, or just optionally if you really feel it and you got this deeper understanding of the formula, okay. And this is why you can imagine that challenge in translating from English to formulas is that we give you this format so often, and it's up to you to translate it to this one. Well, this is a bit easier usually. And then after you do this technical reading, you can translate it straightforwardly into the logical formula given above. Okay, good. So let's consider another example. So we are adding here a new predicate, the C of X representing that X has a computer, okay? And we have this formula here. So clearly we can say that any student, either he or she has a computer, or he has a friend who has a computer, okay? So you will see that this will come um, um, fluently over the time when you solve more and more exercises and you see more and more examples. Okay, so every student has a computer or is a friend with someone who has a computer. So you can always refine your English sentence to reflect the exact meaning. Otherwise, the direct reading would be something like, for every student X, either okay, or for every student, either that student has a computer or there is another student such that that student has a computer and is a friend with the first student. So, okay, so yeah, sometimes the straightforward word by word reading of the formula, as you may notice, is a little bit boring and may get us a little bit confused. Okay, so if you can, after doing the first reading, if you can transform it into this refined reading, that this would be really perfect. Other exercises to choose the obvious predicates and express in predicate logic. So brothers are siblings. So I recommend that you do this exercise by hand. So just pause the video, go to the slide number 10 and do it on your own. I'm gonna do just the last one with you actually. So this one is straightforward. So every X and Y, if X and Y are brothers, then they are necessarily siblings. It's quite similar to the smuggles um, um, and nerds and etc. That the and Flegels, the example that you had at the end of the last deck of slides. So it's quite similar, except that we are having nested quantifiers here because we have two different variables X and Y. Simply good is symmetric. It means that if S of X and Y holds, then necessarily S of Y and X holds too, and vice versa. Everybody loves somebody. If you're using the predicate L to denote that L of X and Y holds when X loves Y, well, this is not a symmetric relationship. Then in this case, if you want to say that everybody loves somebody, then you can say that for every a person there exists a Y such that that person loves Y. There is someone who is loved by everyone, where this is the inverse, okay? Order of nested quantifiers. There is this particular Y such that for every X, that X must necessarily loves Y. There is someone who loves someone, just two existential quantifiers. And the last one, everyone loves himself, So for every x, love of x and x, sorry, so just the last one is here. Everyone loves exactly one other person. Do you remember when I told you that we do not allow ourselves to say that there exists exactly one y such that loves x and y, okay? But rather, so we do not allow ourselves to use this operator, but we can rewrite it in a slightly different way. We can say that for every x, there exists a y such that love of x and y, and for every z such that love of x, z, okay, necessarily z is equal to y, okay? Y must be equal to z. So you can write it in this way. Or you can dually see it as for every z, if z is different than y, then necessarily not love x z. Okay, it cannot be the case that x loves z. Okay, well, and this is the contrapositive of this one. Okay, but and they have the same meaning actually. So you can write it as follows. They are using the second format here. So for every x, there is a y such that if x loves y, such that x loves y, and for every other z, if z is different than y, then it cannot be the case that x loves z because x loves only one. Okay, so here you are saying that there are some, and with this one you are saying that y is unique. Okay, y is only one. Okay, in the exercises you will also be asked to prove that there are exactly two elements satisfying a certain property. Okay, think about it, and then you will see it in the solution, and we can discuss it on Thursday. Negating nested quantifiers, I already talked about this, so it follows the same rule, okay, of negating statements involving a single quantifier, but we apply this rule successively. Okay, so example, if you want to say that there is no woman, okay, there are no women who took flights on all airlines, then you should actually you can negate this expression actually, okay, and use the syntactical flipping of the quantifiers to get the final format. So the negation of the statement is that there does not exist a woman who has taken a flight on every airline in the world, and to negate it actually you should say that for every woman, okay, there exists at least one airline such that for all the flights operated by that airline, it's not the case that that woman has taken any of these flights from that airline, okay? So again, imagine that we are negating this one, okay? So we're putting not there exists W such that for every A, there exists a flight such that a P of W FA. So to get to this format here, we can do it step by step. So we negate this one, so we flip it, and we put the negation inside, and then we copy this part here. You have not for every A, there exists an F such that P W F A. I'm sorry, comma A. Then you can get the negation inside once again. So for every W, there must be an airline for which it's not the case that there exists a flight such that PWFA. And then the last step, you get to this format here once you get the negation inside. Okay, so this should flip. If it is not the case that there exists a flight, then it means that for every flight, it's not the case that P of WFA. Okay, and finally you get this format here. So with this example, I think you will be ready to negate any predicate logic expression with any sequence of nested quantifiers because it's the same rule of flipping the connectives. See you in the next video about inference rules, which are actually the essence of this part about logic.